Now, let us start with the next part in our lecture series, the foundations of quantum computing. And the quantum computing stuff is founded on the principles of quantum mechanics, which were already introduced, and I will relate to them later on. Let's start again with the classical world. The world of Aristotle, classical logic. Classical logic with two values, true and false, represented here by 0 and 1. And perhaps you know the logical connective can be defined by a truth table that was, for example, done also in philosophy by Wittgenstein in his Tractatus. And I will not go here into details, the AND connection and the OR connection. The OR connection is remarkable for further discussion in quantum logic, because here three different inputs have the same output, 1. And that means that this operation is not reversible. If you have 1, you don't know what was the input. And that is crucial for quantum, the quantum computing issues, because all operations later on, we will see that in the quantum formalism are reversible. Now, here, that's also perhaps interesting, but I assume you all know that these connectives in logic at first can be combined. For example, here, the if-then connective can be defined following the truth tables by a connective with negation and here the OR connective. The point is here that these logical connectives in classical logic can be realized technically. And I remember at school when I heard at first about this technical realization, I was excited by that, because perhaps I had my first idea of artificial intelligence, namely that logical thinking can be at least simulated by technology. That is very simple. Perhaps you know that we have to find a technical interpretation for the truth values 0 and 1. Perhaps that can be realized by lamps, lamp off and lamp on. And here are again the technical gates which are directed by the truth table values. I will not go into details, the NOT gate, the AND gate, the OR gate, the exclusive OR gate. Perhaps interesting here, the swap gate, because it exchanges the inputs here, X and Y, to Y and X, and the copy gate. The copy gate seems to be very trivial in the classical world, but actually it is impossible to realize the copy gate in the quantum world. Why? It would be a contradiction to Heisenberg's uncertainty principle. And that is very easily to understand. If you assume in the quantum world a copy gate, then you can make a copy, for example, of a photon. And then you have two photons, the same photon, and in two versions, representations, and then you can make measurements of location with increasing accuracy and measurements of momentum with increasing accuracy independently from one another. And that would be a contradiction to Heisenberg's principle, because they are interrelated and independent on Max constant. Now, let us consider the next step in the classical world. You can, in logic, combine these connectives in order to get more complex are formulas of proposition logic. In technology, you can connect these gates, which I mentioned before, and generate more complex circuits, electronical circuits. And this is a simple example for such a circuit. I like that because that may be also the situation of Leibniz. Perhaps you know Leibniz constructed technically, mechanically, a calculator machine, for example, for addition. And you all know that if you add, for example, in the first column, now in the decimal number system at first, 7 and 5, then you get 12. But you can only note in your column 2. And the value 1 is a carrier value. And the same is true for the binary system that was also considered by Leibniz. If you add 1 and 1, then in the binary system, you get 1, 0. And so again, in your column, you can only write down 0 and 1 is a carrier bit. And that is realized here. In the Leibniz realized it in a mechanical way and with gears and so on. But here, in an electronic way, we combine the exclusive gate with the AND gate. And very easily to understand, here is the corresponding truth table. And here, if you consider the two inputs, 1 and 1, then following the exclusive gate, we get 0. Why? Especially the exclusive gate excluded the situation of the same inputs here. And this is the AND gate with 1 and 1. It leads to 1, of course. In logic, both parts of the formula are true, and then the whole formula is true in that interpretation. And so here you get 1. And that is the carrier bit. And so this simple circuit realizes exact the so-called half editor. And then you can go on and connect a lot of gates. The point is here that in logics, in classical logic, it is well known that we can generate more complex formulas by combining these gates, and that can also be realized technically. But some of these gates are distinguished because they are sufficient to generate all possible circuits, and therefore they are sometimes called universal sets. For example, here the AND or NOT and copy gate. And that is technically interesting, not only logically, because it is sufficient to create these special technical gates, and then, like building blocks, you can combine them to get all kinds of other circuits. Now the quantum world. In the quantum world, at first, we have to interpret what 0 and 1 physically should be. And therefore, an example, there are a lot of technical realization in quantum physics nowadays. We choose a photon again. And here, that is well known to you in summertime with your sunglasses, the photons can be polarized. And here we can distinguish the two states, namely vertical and horizontal polarized. And now superposition comes in. That means there is not only the situation of exclusive values, 0 and 1, but in a superposition, we can also consider all these degrees between 0 and 1. And that is mathematically represented by a vector. And you all know vector geometry from school. And perhaps you remember in vector geometry, we need a coordinate system. And then the vector is defined with relation to these coordinates. For example, you have two coordinates, and then the vector with the origin here in this coordinate system. And that is done here. The vectors are here distinguished as our values 0 and 1. By the way, this notation of vector is typical for quantum physics. It's a notation of Dirac, these brackets. I will not go here in the mathematical details. It is sufficient to understand this notation means the states or the values here are geometrically vectors. And then you get a vector psi in order to describe the superposition, which I mentioned before. And that is represented here with relation to these two coordinates, 0s and 1, with these two components, A0 and A1. Now, it only needs simple school geometry to understand what is going on here. If you imagine now the coordinate system with the coordinates 0 and 1 and the vector in the sense which I described before with the origin of the vector in the intersection of these two coordinates, then this vector can be nearer to the coordinate 0 or nearer to the coordinate 1. And that leads us to a crucial interpretation. You can imagine that this vector in a rectangular coordinate system also forms with these coordinates a rectangular triangle. And that is the situation of Pythagoras. You know, this old theorem of Pythagoras. And if you assume that the vector has the unit length 1, then it is very easily, in the sense of the theorem of Pythagoras, that the sides of this rectangular triangle to the square is 1 to the square. Here, that is Pythagoras, nothing else. And these are these components here. That means you can interpret now this equation. That is a measure for the probability. It indicates the distance to the coordinates. And that, in another interpretation, means probability to be in the state 0 or probability to be in the 0, 1. For example, psi means that now my state is with a probability of 60%, let us say 60%, 0, and with the rest probability, 40%, it is 1. So that is simple school mathematics, nothing else, to find a nice representation of the intuitive representation of a vector state here in quantum mechanics. Now the superposition is crucial for the modern ideas of quantum computing. Why? You cannot only superpose 2 bits, you can superpose unbelievable bits, finite bits that may be billion of bits. In a classical computer, bit by bit, in your laptops, in your smartphones, in the supercomputer at the Leibniz computing center in Garching. All these classical digital machines must elaborate each single bit after another. In a quantum computer, all these bits, a finite number of bits, can put together in a superposition. That means in a common quantum state. And then the computational device is applied to the whole superposition. That is the point. And you can imagine that that leads to an enormous acceleration of computing, and we can use and do this computing with less computing time. And that, in order to give you a simple idea, even from a precise point of view, let us consider, in the classical case, this sequence here of bits: 0, 1, 1, 1, 0, 1, 0, 1, 1, and so on. And now we apply the non-gate, negation. And now this is the result. That means 1 is exchanged, 0 is exchanged by 1, and so on. And we got this sequence. Now, in a quantum computer, a quantum bit is in a superposition state. Remember our vector state, psi. And here with the probability distribution. And now you apply the gate operation, the non-gate, to this superposition, psi prime. That means that 0 is exchanged with 1 and 1 is exchanged with 0. What does that mean? It means with only one application of a gate operation, 2 manipulations are already realized. 2 manipulations. Now we go a step further. Let us consider a superposed state of 2 quantum bits. That is represented here, psi. We have these 4 cases here, 0, 0, 1, 0, 0, 1, 1, 1. And then you again apply the non-gate. And that leads to psi prime. And now here the corresponding manipulation. So that means with 2 qubits, 4 manipulations are already realized by only one gate operation. And of course, that can be generalized. That means 2 to n manipulations are already realized by only one gate operation, and so on. I think that gives us a precise but elementary impression of the enormous acceleration of computation of a quantum computer, and that is sometimes called quantum parallelism. Exactly this situation, application to of the computational devices to superposed states. Now we have to understand what a quantum computer is. A classical computer is nothing else than, let me say, a box of classical gates. Classical gates which are founded by the logical connectives in classical logic. Nothing else. And in the same sense, a quantum computer is a box of quantum gates. But what are quantum gates? At first, let us remember quantum bits can be represented as state vectors. And that is here illustrated in a famous picture in the so-called Bloch sphere. The idea is, in the 3-dimensional space, you have again the coordinate system with the coordinates x, y, and z. And then in the origin of this coordinate system, there is a center of a sphere with a unit radius. And that is illustrated here, the sphere. And on the surface, on the sphere, these points represent all possible quantum states. And then there is a vector which is moving around the center here and is indicating to these points on the surface, that means to the quantum states. At the poles of our sphere, there are our distinguished bits, quantum bits, 0 and 1. And here is the vector, and this is a special situation. The vector has equal distance to both. And that means, in the interpretation of probability, that with equal probability, the vector indicates a situation with equal probability 0 or 1. That is exactly the situation of Schrödinger's cat, you remember? With equal probability, the cat is dead and alive. That is represented here mathematically very easily to understand. With equal probability means that the probability in both cases is 1 to 2, 1/2. And 1/2 plus 1/2 is 1. You remember this simple equation founded by the theorem of Pythagoras. And now this expression to the square relates to the component here. And therefore, we have to calculate the root of this value. And therefore, this component here, 1 divided by root of 2 for both components. That is a special situation, but when it is wandering, then it is changing. I will not go into details. This is the corresponding mirrored states. The point is that these vectors, state vectors, are interpreted in the quantum formalism as so-called operators. And that is only now the information for you. The operators in the quantum formalism must be reversible. And that is a first main difference to the logical connectives in the classical world. You remember the OR connective, I highlighted it in the beginning, which is not reversible. And the point is, and that is mathematical called so-called unitary operators. For us now, it is sufficient to remember that means reversible operators. Now, in a quantum computer, these operators, these quantum operators, are interpreted as quantum gates. Let us have some example. I think that is better to illustrate for you the understanding of quantum gates. Very simple examples. The so-called X operators. It's related, you remember this coordinate which I introduced to define Bloch spheres. The X operator is very simple. It relates to classical NOT gate, negation, and it is flip-flop. Here it means the operation jumping from one pole to the other, 0 and 1. And that, of course, needs a mathematical representation. And the idea is here that the operators, mathematically, very roughly speaking, are represented by matrices, such as this simple matrix. And a quantum bit here with the value 0 means that for two values, 0 and 1, these two values are distributed in one quantum bit, and that leads 1 to 2 to 1, the two values, and then only one quantum gate leads to a representation in a two-dimensional vector space. So the quantum bit here is represented by two-dimensional vectors, here as so-called column vectors. And this is our representation of the operator, and that is simple school math. You have now to multiply the matrix here with this vector space. Perhaps you remember that is doing by adding and multiplying here line with column, line with column. Then you get these values. And in the end, the representation, the two-dimensional representation of quantum bit with the value 1. And that is all. And technically, now that was a mathematical representation, and the technical symbol for this kind of gate is here for later on for constructing more complex circuits. And then in that way, I will not go into details, the Y operator, the Z operator can be introduced, for example, also an operator describing the rotation, you remember, in the Bloch sphere of the vector. And then an amazing new operator. It is amazing because it is typical for the quantum world, and there is no correspondence to the classical world, a logical classical operation. And that is the so-called Hadamard operator. Again, the operator is represented by this kind of matrix here. And now we can calculate, simple by matrix calculation, the application of the Hadamard operator again to the quantum bit with 0, then to the quantum bit with 1, and that is here. Here is the Hadamard operator. Here again the two-dimensional representation of the quantum bit, and simple calculation leads to this expression. And that is a well-known expression. Do you recognize this expression? That is the superposition. That is Schrödinger's cat with equal probability for 0 and 1. And that is the superposition. So the Hadamard operator generates superposition. And therefore, this Hadamard operation is crucial because superposition is a main advantage, remember, quantum parallelism of quantum computing, and that is represented technically for later on circuits by this symbol. And now let us consider a simple application of a two-array operator for two-array qubits. Here, 2 qubits. And now 2 qubits, that means that the two values, 0 and 1, two qubits, mathematically 2, 2, 2, and that is 4. That means the representation of the two quantum bits here in a four-dimensional vector space. And that is done here for the swap operator. You remember the swap operator exchanges the input 0 and 1 to 1 and 0. And exactly that is done here by simple matrix calculation. And that is the corresponding notation of the quantum gate. And now a very remarkable second operator, the so-called controlled net operator, C0 operator. Controlled mean it needs two quantum bits. The first one is called the control quantum bit, and the second one the target quantum bit. And that means if the control qubit is 0, then nothing happens. But if it is 1 here in that case, then the target quantum bit is negated, and that is here, 1. Again, simple calculation. This is a matrix representation of this quantum operator, and this is the symbol of the quantum gate. And the last one I want to highlight, a 3-array operator for 3-array qubits. That means here 3 quantum bits, and you remember we have the two values to distribute, 0 and 1, now to 3 quantum bits. So mathematically 2 to 3, and that is 8, and therefore we consider here the representation in an 8-dimensional vector space. Simple calculation, this is the representation of the C0 operator, leads us to this value. This is the quantum gate. The Toffoli operator, and that was the last one which I like to mention here, is crucial because you remember in the classical case, we have these distinguished sets of gates which are sufficient to construct all other more complex gates. And here in the quantum world, the Toffoli operator is significant because it turns out that you can construct all kinds of quantum circuits by some combinations with the Toffoli operator. And that has practical consequences. The Toffoli operator is crucial for the technical construction of quantum computers, because with a skillful combination, if you have a technical realization of the Toffoli operator, you can construct all these other possible circuits. And that's now all. I come to the end in this section. Now you have already a nice, even in the elementary sense, mathematical, precise understanding what a quantum computer is. A classical computer means you have certain layers, the input layers and the output layer. And between them, there are other layers, and these other layers means logical, the classical sense, gates. And what is a classical algorithm? It is nothing else than a sequence, than a connection of classical logic gates. And that is represented in the computer. And that is also true here in a quantum computer. Very simple. Now from left to right, you have at first the input layer. The input layer with the bits. The bits are represented here by arrows up and down. And then, of course, we like to use the advantage of a quantum computer. That's quantum parallelism. And therefore, we need superposition. And that is realized by the Hadamard operator. So in the second layer, application of the Hadamard operator. And then we have superposed the states, and then we can apply for the different quantum algorithms, sequences of these quantum gates, of course, more than the quantum gates I mentioned before, in combination. And in the end, you get, of course, a superposition with all the possible results. And then remember the Schrödinger situation. Then we have to measure the superposition. And what does us tell the Schrödinger situation? If we measure the superposition, then the superposition collapses spontaneously in all possible results. In the Schrödinger case, only 0 and 1, dead and alive. But here we have several, for n elements, superpositions of possible results. And if we measure that, that is indicated here by these building blocks with the scaling, that means measuring. In the end, then the superposition decays with all these results. Now that is a difficult situation, because what should we do? Of course, we could check, and that is a stupid way, check each result if it is right or not. But then we lose all advantages of quantum computing and acceleration. So the point is here to find a reading out algorithm for the correct result in the superposition, which is provided by the quantum computer. Now, a first algorithm was the so-called Grover algorithm. And the Grover algorithm can actually improve the calculation time in an ordering of root of n. If n elements, now in ordering of root of n. That's, of course, an improvement, but practically it cannot realize in practical computational time nowadays. It is only theoretical interesting. So later on, better reading out algorithms were suggested. For example, the fast Fourier algorithm, which is in technology, engineering, sciences, very successful, but in a classical way, and that must be translated into a quantum formalism. Anyway, for us today, the information, there are these kind of algorithms reading out the correct results in a practical time. And with that vision and understanding of the quantum computer, I like to close this section. Thank you.